Okay, so we're still looking at double integral on a region f(x1). Okay, and last week we discussed the case where the region is in the polar coordinate system, so it is equal to the angle is bounded between alpha and beta. R is bounded by A and B. So this is so-called a polar rectangle. So it is bounded by two rays coming from the two angles alpha and beta, and two distances coming from A and B. So this is alpha, the larger angle is beta, and you can look at the distance between this is A, and this distance is B. Okay? So this is the region we're looking at, and this is the region we're taking our integral on. And if it is written in this form, it can be integrated by using alpha and theta. So from A to B, and then we have to change the variables x to y to r and theta naturally. Okay? So the formula we're using is r cosine theta, r sine theta. And do not forget about this extra factor coming r. Okay, so this will be our formula here. Okay, so and also we discussed several different analyses where this polar coordinates has a lot of advantage over x and y coordinate system. Right? For instance, I gave you an example to compute the area of a disk. In the polar coordinate system, it's extremely easy. Right? As long as we can identify the x. As long as we can identify alpha, beta, A, and B for this polar rectangle. Okay, so I want to practice a couple of more examples. Okay, and I want to give you a general feeling, because now we have a rectangle as the region, we have x simple region, we have y simple region, we have a polar rectangle as region. So given a double integral, which ones you want to try polar coordinates? Right, I want to give you a feeling of more or less a general principle, which kind of integrating function, which kind of integrating region you really want to try polar coordinate system. So I want to take the double integral from e to minus x squared minus y squared dA, where the region is given by x squared plus y squared is less than or equal to 16. Okay. So this is the one. So one of the biggest principles we're going to use is the following. Probably you already got this as right. So as long as I'm looking at my integral, so the function contains x squared plus y squared, or the integrating region contains x squared plus y squared, it is a pretty clear sign that I want to try to use polar coordinates. Right? In polar coordinates, one of the most important formula we should keep in mind is r squared equals x squared plus y squared. Right? So this is one of the most important formulas to link x, y coordinate system to our theta coordinate system. Therefore, if I see x squared, y squared, x squared plus y squared, this is a clear sign I want to try polar coordinate system. Right? In order to do that, I need to translate this region into a polar region. Okay, right? I need to translate this into a polar region in which I need to identify the smallest angle, the greatest angle, the smallest distance, and longest distance. All right? And a very helpful way to do this is to easily sketch the region here. And as I said, you don't have to be super precise, but at least you have to have the key information here. So x squared plus y squared is less than or equal to 16. This is a disk with center 0, 0, radius 4. So this is the region. Okay. If I want to identify this region as a polar region, the angle is going to vary from 0 to 2 pi. 0 to 2 pi will cover the whole plane, all right? And the radius is going from 0 to 4. All right? It's going from 0 to 4. And then I needed to switch from x, y to r and theta. And this is pretty simple. And this is indeed one of the hints we begin from. So e to minus x squared plus y squared. But we have this as r squared, right? This is r squared. And then we have extra r coming out, dr d theta. So in the end, I'm getting the integral from 0 to 2 pi from 0 to 4 e to minus r squared multiplied by r dr d theta. Imagine if you want to translate this double integral into an x simple or y simple region. Listen carefully. You can't do that. Am I right? And we have done that before. I can identify this as a y simple region where x varies from -4 to 4. Y is bounded between a lower function here and an upper function here. You can't translate this. You can identify this region as a y simple region. In fact, you can also identify this region as a x simple region, right? Y varies from -4 to 4. X changes from the left to right. But imagine if you want to try to find the antiderivative for this function, where x and y is the variable. It's pretty challenging, right? We know the antiderivative for e to minus x. But e to minus x squared, we don't know what the antiderivative is, all right? So on one hand, in the very beginning, I already decided to use a polar coordinate system because I see x squared plus y squared. On the other hand, it is really quite easy to doing this polar coordinates comparing to x and y because finding the antiderivative is quite challenging here, okay? So if I'm trying to find the antiderivative, this guy is much more simpler, right? So from 0 to 2 pi, e to minus r squared r, the antiderivative should be e to minus r squared, but I need to cancel minus 2 here. So it's going to be minus half of this, right? Still, if you're not fully convinced that this is the correct function, what do? You take the derivative and see whether you can end up with this function again. You take the derivative exponentials, it's going to stay, so it's e to minus r squared. And then you pull up minus 2r, right? Minus 2r will cancel minus 2 here, and r will remain here. So this is indeed the antiderivative, all right? So this is the antiderivative. I'm evaluating from r equals 0, or equals 4, d theta. And also, I mentioned this a couple of times, because we're dealing with a lot of variables, when you take the antiderivative and then evaluate at the boundary points, I usually want to keep this variable in my evaluation to remind me I'm actually taking the value r as the number I want to plug in. Okay? So keep this r with you because you also have this theta as the variable in the outside. So I'm plugging in r equals 0 and getting from 0 to 2 pi r equals 0, I'm getting a minus 1/2, right? So exponential when the exponent is 0, so it's just a 1. Minus when r equals 4, I have minus half of e to minus 16.
Isn't it? I have a question. Isn't it 4 minus 0?
Am I doing it again? I think so. Sorry, so I'm supposed to have minus half of e to minus 16 minus 1/2.
Yeah.
Right? So this is the theta. Okay? So the inside is nothing but half of 1 minus e to minus 16, right? And then the antiderivative is this constant multiplied by theta, and then I'm evaluating from 0 to 2 pi. Or if you have done this so many different times, if the inside integrating function has nothing to do with the variable, this integral is just this constant multiplied by the difference between the two boundary points, all right? It's nothing but this constant multiplied by 2 pi, because the integrating function is a constant, right? Multiplied by 2 pi. So this is just pi 1 minus e to minus 16, okay? Okay, so this is one of the very nice applications for polar coordinate system, which it will be pretty hard to evaluate this double integral in x simple or y simple region. And also, I want to make one remark about this kind of examples. We have this interpretation of double integral, what double integral means, right? So when I'm looking at this number, I actually have one interpretation of this number is about the signed volume above this region below this function, right? In other words, if this function, the surface of this function stays above xy plane, the volume should be always positive. In the simplest form, I'm saying if I'm integrating a positive function, I'm supposed to get a positive number. No matter what number I have to make sure at least it is a positive number. So this is a very useful way to check whether your computation is at least correct in principle. So if your integrating function is positive, this is indeed a positive function, all right? Exponentials are always positive, right? Exponentials are always positive in the end. I have to get a positive number. This is why e to minus 16, I don't know exactly what it is, but this is definitely less than 1, all right? So this is definitely positive. So at least I know my number is in the correct sign, okay? And this is pretty useful to see whether you are having the right number or not. You don't know whether this is precisely correct, but at least you have to make sure the sign is correct. If the sign is wrong, your whole computation, no matter what you do, you can switch to X simple, you can switch to Y simple, you can switch to whatever you want. In the end, if your sign is not correct, the computation is definitely not correct, okay? So you can look back and see if your function is positive, then you have to make sure your answer is a number, is a positive number, okay? And this, I would say, is a pretty useful trick I use all the time to check whether my answer is at least in the correct direction. Questions? So this particular problem, I have the integrating function. I also have this region to be quite explicit. There are some other problems you have to extract the information for the integrating function and then identify it as a polar region. So this is the next example. So I want to find the volume of the solid bounded by 30 minus 4x squared minus 4 y squared, and z is equal to 14. Okay? So I want to find the volume of a solid bounded by these two surfaces, basically. So testing again. What is this surface? So z is equal to, what is this surface?
The hyperbola of two sheets.
This is a elliptic paraboloid opening downwards, right, opening to the negative direction of the z-axis. Okay, so basically it will look like this. So opening downwards with vertex 0, 0, 30. So open downwards. This will be the rough picture. Okay, and then what is this surface? This is a plane at height 14, right? So this is 30. Then this plane will cut through the parabolic at the height 40. I'm sorry, 14. Okay, this is 14. So naturally, if you cut through this parabolic by a plane, you're going to get a. What is the word I'm looking for? Level curve, right? This is actually a level curve, right? So this is the level curve of this paraboloid at height z equals 14, okay? And if you cut through, you can actually find the equation 14 equals 13 minus 4x squared minus 4y squared. And this one defines a circle, right? This one actually defines a circle. Right? If you want, you can simplify it to 4x squared plus 4y squared is equal to 16. So x squared plus y squared is equal to 4. So this is actually a circle centered at the origin with radius 2. Okay. So this is indeed if I'm looking at the intersection between these two surfaces, I'm getting a level curve as a circle with radius 2. Okay. Strictly speaking, in order to identify this as a level curve, you have to project this back onto the xy plane. Remember? So in the first midterm, I gave you the question of finding the level curves. Right? So essentially, you have a function, and then you have different levels. You're supposed to cut through this and get a level curves on the xy plane. Okay? As I said, after the midterm, you don't want to throw away what you learned in the first 1/3 of the semester. Okay? So I want to constantly remind you what we learned before. Here, I want to remind you this is a level curve, but also this is quite useful as well. As long as I have the sketch of these two surfaces, I know the region I'm supposed to compute the volume for the solid is bounded between these two. So it's above the plane and bounded by the paraboloid. All right, so this is the solid I want to compute the volume for. regardless of what this region is, I can immediately write down what the volume is. The volume is supposed to be a double integral of something over difference between these two functions, right? So the difference between these two functions is 13 minus 4 x squared minus 4 y squared and minus 14. So regardless of what this solid is, at least I know it has to be a double integral. And we have done this before, right? So we compute the volume of the solid below 1 and above the other two. So the volume bounded between these two surfaces is the integrating of difference between these two functions. So the key thing here is still how do I figure out where this region is, all right? So this is the key thing. I have to identify where this region is and then put it into x simple, y simple, rectangle, or a polar region, okay? So all the questions you will see in the beginning are basically just a simple double integral. So I give you the intervening function, I give you the intervening region, and then you just evaluate the double integral. But eventually, you will look at these kind of problems where you have to extract the information by yourself. And then you're going to have to use the double integral to evaluate whatever they're looking for, okay? So here the key point is how to identify this region. So this region is definitely going to be the intersection between these two. At least it is related to the intersection between these two surfaces, all right? So I already found the intersection between these two surfaces is indeed this curve, which is a circle right here. So the intergradient region is supposed to be what is inside, all right? I have found the intersection of these two surfaces, but when I'm looking at the intergradient region, I'm supposed to have a region in the xy plane. This is the very first thing we agreed on for double integral. For double integral, we're supposed to have a function, and also you're supposed to have a region in the xy plane, all right? This is only a circle, it's not a region yet, but it is not that far away from